Okay, let's look at Chapter 7, Review for Test. Number 1, what is the centripetal acceleration? So I want to find AC of a ball traveling at 6 meters per second, so that's V, in a circle whose radius is 9 meters. So we're going to use our equation. Centripetal acceleration is v squared over r. So it's going to be 6.0 meters per second squared divided by 9 meters. And when we do that on our calculator, it comes out to be 4 meters per second squared. And again, we can carry our units through to check our work. So in the numerator, we're going to have a meter squared over a second squared divided by a meter, which is the same as a meter squared over a second squared times 1 over a meter. So this cancels with that, and I end up with meters per second squared, which is the correct unit for acceleration. All right, number 2. If the velocity of a car traveling around a circular track doubles, what happens to its centripetal acceleration? So the answer to number 1, whoops, this one was D, 4. Number 2, so I'm going to look at my equation. Centripetal acceleration is v squared over r. So now they're saying what happens if the velocity doubles. So that's this. So now I have centripetal acceleration is 2v squared over r. So when I multiply that out, it becomes 4vt squared over r. So the difference between this and this is 4. So the answer is 4 times as great. So the answer there is D. Number 3, an object is moving with a constant speed in a circular path. The object's centripetal acceleration remains constant, and again, it's the magnitude, because if I look at something, so if the velocity, remember the velocity is the tangential velocity, so as it's moving, this is the way at this one and one only point my velocity would look. And then the acceleration always acts towards the center. So again, the acceleration is also changing direction. So only the magnitude remains constant, not the direction. So the answer there is A. Okay, number 4. In the diagram below, a car travels clockwise at a constant speed in a horizontal circle. At the position shown, which is right here, which arrow indicates the direction of the centripetal acceleration? So the centripetal acceleration always acts towards the center. So it's going to be like that. So the answer to number 4 is going to be A. Number 5. An object traveling with uniform circular motion has a centripetal acceleration due to the change in, so the answer is the direction, because as we saw in this other picture, the speed is constant, but the direction changes. So the answer here is B. Number 6, an unbalanced force, so that's my F, so let's go ahead and write that the force is 40 newtons, keeps a 5 kilogram object, that's the mass, traveling in a circle, and R is 2 meters. What's the speed? So this is our given. We want to find V sub t. And when we think about the relationship, we know that the centripetal force is equal to mvt squared over r. Now we want to solve for v. So I'm not going to plug in. I'm going to rearrange the equation to solve for the unknown in terms of the known. So I'll multiply both sides by r, and then I will divide by m. Then I'll take the square root of both sides. So now I have the square root of FCR over m. Then I'll go ahead and substitute in my value. So I have 40 newtons, and a newton is a kilogram meter per second squared, times R, which is 2 meters, divided by the mass, which is 5 kilograms. Now, remember, in physics, you have a foolproof way to always check your work. So this kilogram cancels with that. A meter times a meter is a meter squared. So when I take the square root of the number, I take the square root of the unit. So the square root of meter squared over second squared is meter per second. So I know I didn't make a mistake. And when I do this on my calculator, I get 4 meters per second, which is D. Again, if I rearrange the equation and carry through, I have a foolproof way to check my work. Okay, let's move on to number 7. Number 7 says the path of a satellite orbiting Earth. So this is going to be an elliptical orbit, and this is Kepler's first law. Kepler's first law, again, says that orbits of the planet are ellipses with the sun at one focus. So remember, in a circle, we have a center, but when we have ellipse, there's 2 foci, and the sun is at one of them. And that's Kepler's first law. Number 8, a 1.0 times 10 to the 3 kilogram car travels at a constant speed. Now, I have all this information, but now that I look at the choices, I'm literally just looking at the diagram, so I don't have to do a calculation. Okay? So it says which shows the correct direction of the centripetal force and the velocity. Well, first of all, we know that the velocity, v, is always tangent to the curve. Here, v is going into the center, so that's wrong, and that's wrong. So right away, just from the velocity, I know this is correct. We also know that the centripetal force always acts toward the center. But this one was too easy because I didn't even have all those. All right, number 9. The shapes of the paths of the planet around the sun are, okay, these are ellipses with the sun at one focus, and this again is Kepler's first law. And we forgot to write that number 8 was A. All right, let's finish this up. Number 10. Base your answers on the following question of the diagram below. So a planet P moves around the sun S in an elliptical orbit. The amount of time required for the planet to travel from A to B is equal to the amount of time required from C to D. Compared to the areas of ABS, the area of CDS is. So this is Kepler's second law. Kepler's second law says a line connecting the planets and the sun sweeps out equal areas in equal time. So this area is equal to this. And if you remember in class, we talked about conservation of energy. So the time it takes to go from here to here is equal from the time to go from here to here, because again, when we're closer to the sun, we're moving faster, and when we're further away, we're moving slower, but the areas are equal. So the answer to number 10 is C, the same, and this is Kepler's second law. All right, number 11. For planets orbiting the sun, the ratio of the mean radius of the orbit cube to the orbital period of motion squared is, so this is Kepler's third law. Kepler's third law, if we put it in an equation form, it's RA over RB cubed is TA over TB squared. So this is the average distance if this is planet A and planet B cubed, and then T is the periods. So the answer to number 11 is D. And this is Kepler's third law. Okay, number 12. The centers of two 15-kilogram spheres are separated. What's the magnitude of the gravitational force? So M1 is equal to M2 is equal to 15 kilograms. The distance is 3 meters. So the gravitational force F of G is equal to big G, the universal Newtonian gravitational constant, M1, M2 divided by R squared. So that's going to be 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times 15 divided by 3.00 meters squared. When we do that on our calculator, F of G comes out to be 1.67 times 10 to the negative 9 newtons. So the answer there would be C. Number 13, if the mass of two objects is increased, the force of attraction between them will. So this is where we look at our equation, okay? So here's our equation, F of G is big G, M1, M2 over R squared. So it says if one of the two objects, if the mass is increased, so that means let's just pick M1. So let's say this increases. What happens to this, the force? Well, this is in the numerator, so the mass is directly proportional to this gravitational force. So as this increases, that increases. So the answer to number 13 is going to be B, because they're directly proportional. Okay. Number 14. Two objects of equal mass are a fixed distance apart. If the mass of each object could be tripled, what happens to the gravitational force? Again, our basic equation is F of G is equal to G, M1, M2 over R squared. So now they're saying each of the masses is tripled. So now if I look at this equation, now I have 3M, I'll still call this M1 and M2 over R squared. Now I'm going to multiply this out, so I have big G, 3 times 3 is 9. Then I still have M1, M2 over R squared. So the difference between this and this is the 9. So the answer there is 9 times, increases by 9 times, D. And number 15 says which graph represents the relationship between the magnitude of the gravitational force between two masses and the distance. So again, first I'm going to look at my equation. And if you look at my graph, here's my force. So as R increases, what's happening to F? Okay. So if this is getting bigger, this is going to be getting smaller, but the thing is this is squared. If this wasn't squared, it would be inversely proportional, which would be a straight line. But because there's a square, it has to be a curve. And then to know the relationship, if this increases, because it says as R increases, because as I go from left to right, this is going to get smaller. So as R increases, f of g decreases exponentially. So that answer is going to be D. And again, you understand that by just looking at the equation and looking at the relationship between the values in the equation. Again, because R is squared and in the denominator, that's how we know it decreases. And because it's squared, that's how we know it's exponential and not linear. And that's it.